Hello everyone, and thank you for joining this webinar. My name is Ben Schmidt. I'm an XPS staff scientist at Physical Electronics. And today the topic will be ion gun options and capabilities on the PHI XPS microprobe system, specifically talking about our VersaProbe systems. So what I'd like to do to introduce this topic is to provide a little bit of motivation for how we use ion guns in our surface analysis tools. Typically the applications are twofold. First, because we're dealing with surfaces, just handling them in atmospheres can create a layer of adventitious material on the surface that can degrade our signal that we want to analyze. And so we may be interested in just trying to clean off this adventitious material to get to the material of our interest. We also may want to do deeper profiling into a sample to look at layer structures, compositional changes as we go through different processing steps, or other properties that are deeper than the typical information depth of something like XPS. And so when we do these types of processes with ion guns, what are the expectations that ideally a user would have for these materials? What we would like to see is that the ion beam induces no changes to the sample's composition, no changes to the chemical bonding states that we wish to analyze. We would also like to maintain sharp layer interfaces, and we would also like to be able to do this at high throughput with high sputter rates. And so the ion gun options that are available on VersaProbe systems are shown here. There are three ion guns that we can use. The standard monoatomic argon ion gun is standard on the system. That is used both for sputtering and also used for the dual beam charge compensation technology. That ion gun can go from up to 5 kV. We can also use it in a floating column mode where we can generate large currents of ions at low voltages. We also have an optional C60 ion gun using a C60 buckyball as the ion source. That can have a beam voltage up to 10 to 20 kV and is a mass filtered ion beam. We also have an argon cluster ion beam, or GCIB, where we can tune the cluster size from around 620 to around 2500 argon atoms, and that has a maximum voltage of 20 kV, and that is also a mass filtered ion beam. As you can see on the schematic on the right side of a VersaProbe system, we do have the ability to mount all three of these guns on the system at the same time. And so you can choose, based on your application, which gun is going to be most appropriate, and then select the ion guns that is best suited for your work. I would like to point out that we also have just recently introduced a cluster size measurement tool that can be added to the system so that you can create settings and test the cluster size distribution on your own system and use that to optimize the settings for your depth profiling or cleaning experiments. And so to talk about these different ion sources just a little bit, first, the monoatomic argon has been long used in this type of industry for surface cleaning of materials. However, as advanced materials included more organic and mixed type of compositions, we found that argon was just not good enough to maintain the chemistry that we needed. And so PHI introduced a C60 ion source on their XPS systems in 2004. Additionally, we introduced the argon gas cluster source around 2010. And what we're going to talk about over the next few minutes is how we can use these different sources for different types of materials and applications. And with the cluster sources, it does open up a wider variety of materials beyond those with monoatomic argon. And to help us understand why these cluster sources are more useful to us, we can see here simulations of the impact of either a monoatomic ion or a cluster ion on a surface. What you will see on the left is that monoatomic ions tend to penetrate deep into the material, and they create a lot of damage within the material and actually are not that effective at removing material. However, the cluster ions tend to be more sensitive to the near surface regions, creating a thinner damage layer and also providing a more representative surface as we go deeper into the material. And so with these different ion guns, what I'm showing in a table here is our current understanding and recommendation for different types of materials that you may work with in your own research. On the left side, I have groups of inorganic and then organic and polymer type materials, and some different characteristics of using the different types of ion sources, such as monoatomic, C60, or argon cluster. For example, for inorganic materials, we do find that metals are best suited to be analyzed with the monoatomic argon. Oxides or metalloid alloys tend to work best with the C60. And with the argon cluster, we find that materials that contain C60 themselves may be useful, but there are some drawbacks with things like roughening. And we're going to go through and explore different parts of this table with some examples of different types of materials. And we can see that some ion sources are better suited for inorganics, organics, or mixed materials that we will talk about over the next few slides. So to start with, we're going to discuss inorganic materials. And we'll have a few examples of both surface cleaning and what type of characteristics we can get with cleaning of inorganics with these types of sources, and also depth profiling and looking at some of the pros and cons of each of these. So to start with, I have an example showing what happens if we try to clean and actually profile through titanium dioxide with monoatomic argon. This is well known to cause damage and reduction of the titanium as shown by the Ti2P peak. As we start at the top at 0 minutes, we see a sharp peak of the Ti4+ state, but as we continue to sputter with monoatomic argon, there is a peak that develops to the lower binding energy side, which represents damaged and reduced states. So if we wanted to clean TiO2, it may be difficult with monoatomic argon. However, using something like a cluster source, we do see that we can effectively clean the titanium surface without seeing damage. If you look at the Ti2P peak, we see a very small change in the after clean peak, and we can also see that the carbon has been effectively removed and our oxygen peak is more representative of a titanium oxide. Now looking at a metallic sample with the monoatomic argon, this is an example of a multi-point sputter depth profile on a solder bump. Now in our SXI image, which you see at the top center, this is a secondary electron image that was collected by scanning the X-ray beam, and we have a bright region which corresponds to our solder ball, and then a darker region which corresponds to the surrounding area. We can select points directly on this image to choose where we want to do our profiling. And so the spectra that you see below are from the solder bump itself. And going from the front of the figure toward the back, we are going from the surface to the bulk of the material. And for both the tin and the lead that comprise this solder bump, we see at the beginning there is an oxide layer, and as we sputter deeper into it with the argon, we do see a metal as expected. The figure on the bottom right shows us an overall depth profile of this solder ball, and we can see that there is the oxide chemistry and the metal chemistry of both the tin and the lead that we can separate out using curve fitting and LLS, and we can even see that the lead is preferentially enhanced at the top of that oxide relative to the tin even. And so that is an example where we can use the monoatomic argon for sputtering of this material. We can also use higher energy argon for things like sputtering through a multi-layer glass coating. As you can see here, we have multiple layers, and we have very nice interface resolution as we go through the layers. In the spectra on the right side, we see that slight changes in the Si2P correspond to the aluminum-doped silicon oxide near the surface and the silicate substrate. This also shows how we can use additional properties of our profiling, like Zolar rotation, which allows us to rotate the sample during a profile to get a more uniform sputter crater and enhance the interface resolution. We also see that we can use our dual beam charge compensation during this profile to get accurate chemical state information for peak assignments. So now that we have shown some of the advantages of using monoatomic argon for these types of materials, what can we do with cluster sources? What I'm showing here are argon gas cluster GCIB profiles of a hafnium dioxide film. Like titanium dioxide, hafnium dioxide is readily known to reduce under monoatomic argon bombardment. And I have 4 different plots shown, and each of these have a different configuration of the gas cluster beam. For example, the voltage in the top left is a 5 kV beam with a cluster size of 1,300 atoms. And if we look at the then EV per atom, we can see that going from the top left to the bottom right, we have an increasing energy per atom, which is one of the ways that we can control our parameters for depth profiling. And if we look at the change in the spectra as we profile through these materials, we do see that as we increase the EV per atom, we are seeing changes in the spectra, as in reduction of the 4F5 peak and a broadening to lower energy, which is related to reduction of the hafnium oxidation state. In general, lower energy per atom does give us better performance as far as chemical damage related to the spectra, but we often find that that also is seen with a reduced sputtering rate. So there may be some trade-offs of how much damage is okay versus the rate that we want to sputter through for the throughput we need for our analysis. Now this is a busy table, but what we're introducing here is an oxide stack. So we have 3 oxide layers on a substrate that I will show in just a minute, and we're looking at how they compare using these different ion guns for this analysis. The first column shows a 500 volt argon, monoatomic argon that we'll be using. And just like the definition I mentioned in the previous slide, we have one atom with 500 volt beam voltage, so that has an energy per atom of 500 EV per atom. Similarly, we have a 20 kV C60 beam that we will be analyzing this with, and also a 20 kV gas argon 620 cluster. And so we go from 500 EV per atom down to approximately 32 EV per atom. There are some other parameters in here related to the conditions used for this study. And I would also just like to point out, as I mentioned before, the general efficiency of the monoatomic being less than that of the cluster sources, where we can see for each incoming ion, the material volume that is actually removed is least with the monoatomic argon and higher with the cluster sources. And so the stack of materials that we're looking at is a hafnium dioxide on top of a titanium dioxide on top of an aluminum oxide on a silicon substrate. And the figure at the top is using our 500 EV monoatomic argon. The middle one is the 20 kV C60, and the bottom one is the 20 kV argon 620. And at first glance, we can look at things like the composition as we go through each layer. We can look at the interface quality, and we can look at the broadening that we may see. So I'll point out that the stoichiometry for both the C60 and the monoatomic argon tend to be closest to the actual values. In the gas cluster, argon gas cluster at the bottom, we do see, for example, the titanium concentration in the is closer to 20%, where it should be more like 33%. We also notice that in the argon gas cluster, the interfaces are quite broad. And we even see hafnium that is being detected all the way down at the aluminum layer. Whereas for the argon and the C60, the monoatomic argon and the C60, we do see sharper interfaces for each of those. One thing to also note for the C60, there is some carbon that is deposited in the silicon substrate layer, which you do not see with the other two conditions. So as you can see, there are some trade-offs for each of these types of sources related to the stoichiometry that we detect, or the broadening and interface quality. If we also look at the spectra itself from this analysis, we are looking at the hafnium 4F spectrum taken from basically the middle of the hafnium dioxide layer, in addition to the oxygen 1s spectrum. And the plots from top to bottom are the monoatomic argon, the 20 kV C60, and the 20 kV argon 620. As we have shown before, under monoatomic argon, we do see reduction of the hafnium going from a fully oxidized state to a reduced state, as you can see by the broadening of that structure. We do see actually the least reduction from the 20 kV argon 620, which is in line with what we have seen from EV per atom considerations previously shown. Another material system that we have done a comparison on is IGZO, which is an indium zinc gallium oxide. This has multiple components. And we have also done a similar analysis using 500 EV argon, 20 kV C60 and a 20 kV argon 2500 cluster size. We can see several differences between these profiles related to the stoichiometry of the film. For example, in the first two plots you see a difference in the indium concentration. We can also look at the quality of the interface going from the IGZO material to the substrate, whereas it is quite sharp for the monoatomic argon and slightly less so, but good for the C60. However, the argon gas cluster shows very broad interfaces. And so we'd like to investigate that in a little more detail. We can also take into consideration things like the effect of Zollar rotation by rotating our sample and how that can improve our interface quality for these types of profiles. You'll notice that for the Zollar rotation, which is the bold line, compared to the non-Zollar rotated, which is the dashed line, with Zollar rotation on this system, we do see sharper interfaces as shown in the monoatomic argon and the C60 profiles, and also with the GCIB. We can also look at things like preferential sputtering with these different types of guns. When you have multi-component samples like this, the sputter rate of each of the components can be slightly different, and so your overall stoichiometry for the material may not be quite accurate to what your expected values are. So if we look at the start on the monoatomic argon on the left, we can see that the indium concentration is slightly below the 17.8 that we would expect from RBS analysis of this material. For the C60, it is slightly higher than the expected value. We also look at the gallium concentration for C60, which is closer to the 16.9 expected value compared to that of the monoatomic argon. Looking at the argon gas cluster, we can see that in general we really don't even get a uniform concentration through the material, as it seems to always be decreasing or changing. And so from this example, it looks like the C60 has given us the closest measurement relative to that of RBS for the intact material. So related to what we have seen about interface quality, we can look at the crater bottom with atomic force microscopy to understand how that may affect it. This is a 5x5 micron area at the crater bottom of the three different samples that we've looked at with these three different ion sources. We find that the monoatomic argon has the lowest root mean squared roughness, whereas for the argon gas cluster, that has the highest roughness. And so that may be related to why we see broad interfaces. If a rough surface prevents us from adequately sputtering away material in our sputter cycles, then we could see distribution of those materials across layers. We can also zoom into a smaller field of view of approximately 1 by 1 micron, and again we do see more structure in the argon gas cluster crater, showing that higher roughness. So now I'd like to switch gears a little bit and look into a different type of material class, such as our organics and polymers. And we again will start with some examples of how we can clean these materials with different ion sources, and then looking at some of the depth profiling capabilities. To start with, we have a PMMA surface that is showing surface contamination of some silicones. We can clean this off using C60 cluster, for example. As you can see in the Spectra for C1S, once we have cleaned the material off, which is the blue spectrum, we do see more of a shoulder at around 285 that is representative of the structure of PMMA. We also see an increase in the oxygen 1s peak at higher binding energy, which is consistent with that of a cleaned PMMA. We also see the silicon concentration has been effectively removed after the C60 sputtering, showing that we can clean off the surface contaminant but preserve the chemistry of the underlying material. If we tried to do this with a monoatomic argon, we would most likely damage all of these and leave us with just a graphitized carbon. Another example of showing polymer cleaning with the argon gas cluster is here on PET. The as received spectrum is shown in red and has adventitious contamination on it. As we sputter it with argon cluster, we can see that we develop the spectral shape representative of PET. Then if we try sputtering it with a little bit of monoatomic argon, the peaks at 286 and 289 disappear, and we get a higher peak around 285, which is representative of just carbon-carbon bonding. We can actually continue with our argon gas cluster sputtering and eventually remove that damaged layer of material and preserve our original PET spectrum. In another example of PMMA, we can show how monoatomic argon just does not do very well with cleaning of polymer materials. Even at a low energy at 250 volts, as soon as we start sputtering, the oxygen concentration decreases, our carbon increases, far away from our expected composition for PMMA. Looking at the C1s spectrum in the top middle plot, we can see at the surface, which is toward the back of the figure, we quickly lose our spectral features once sputtering with argon. However, with a C60 ion gun, we maintain the composition and we also maintain the spectral shapes for the PMMA. This is an example of a type 2 polymer that is well suited for C60 profiling. These are types of polymers that undergo a chain scission type of breaking up under ion bombardment, such as PTFE, polystyrene, and others. However, polymers that are considered type 1, such as polyimide, can actually cross-link under ion beam bombardment. And when doing so under a C60, that can make it difficult to actually clean or sputter these materials. As you see here in the plot on the left, we have a polyimide film that upon sputtering, we decrease our oxygen concentration, increase carbon, and we're not able to actually sputter through this film. This was one of the ideas that prompted us to develop an additional ion source beyond the C60, which led to the development of the gas cluster ion beam with argon. As you can see here, with a 10 kV argon 2500 sputtering of polyimide, we can sputter through the material and maintain the chemistry. And as I've shown previously on PET, we can also use the gas cluster GCIB to recover from a damaged layer as shown on polyimide when we have sputtered with monoatomic argon. In each of these figures, starting from the top left, we have used increasing energy beams of monoatomic argon and then switched over to a 10 kV argon gas cluster beam. And we can see that even though the composition is not what is expected at the beginning of the profile, as we sputter with the GCIB, we eventually reach the expected composition for clean polyimide. And so that allows us to sputter profile through quite large depths of material. As shown here, this is a blended polymer of polyethylene and nylon, multi-layer structure, and we can sputter through up to 10 microns and beyond while maintaining the chemical structure of these two materials and as well as their composition and stoichiometry. With that, we have talked about inorganic materials by themselves, organic materials by themselves, but a lot of advanced structures that we see now combine both of those, either in layered methods or actually in combination in a single phase. And so how should we approach these complex materials that we tend to see more of in our research? So the first example that I will show is a stack of inorganic layers with an organic layer in between and then inorganic layers below. So we have silver, a molybdenum oxide, and then a polymer layer on top of ITO and glass. In this case, what we are able to do is start with monoatomic argon for the inorganic section of the profile, and then once we start getting into the organic layer, we can either stop the profile and switch to a argon gas cluster, or we can program that directly into our profile ahead of time to change guns and use the argon gas cluster. And therefore we can maintain the chemistry of the organic layer, and then once we reach the inorganic layers below, we can switch back to the monoatomic gun for better performance. For a similar sample, this is again, we have a photovoltaic device which has a silver surface, some organic layers on the top, and then we have actually a mixed layer of organics and TiO2 as an inorganic. What would be the preferred gun to use here? What we've decided to do is use a C60 because we typically find that the argon gas cluster, the sputter rates of organic materials is usually much greater than that of inorganic materials. Whereas for the C60, we find that the sputter rates tend to be more similar. Therefore, we would be sputtering through both of those within that layer at a similar rate, rather than completely removing the organic and leaving behind a skeleton of inorganic material, for example. And so for this particular case, we have found that the C60 is a good compromise for this type of mixed inorganic and organic material. And then we can use the C60 for the entire profile from start to finish. And so what I hope to have shown is that based on different types of materials of interest, there are different factors that may play into which gun is going to be the most appropriate to achieve the answers that you're looking for. And as I've shown here, we have cases where inorganic materials can be best suited for monoatomic, depending on if we're cleaning or trying to depth profile. We can also use cluster sources as well, but we have seen some drawbacks with things like sputter rates and interface quality. Whereas for the organics and polymers, we know that monoatomic argon will cause damage to those materials, but we can use cluster sources to help preserve the chemistry for those profiles. And if we do have cases of mixed materials, then we can either use different guns for different layers within that material, or we can try using a single gun where something like a C60 might be appropriate to match the sputter rates of the inorganic and organic parts to that. And so with that, I would like to thank you for your attention today. I encourage you to visit our website at phi.com to check out the latest news and information. We have recently just announced a European user meeting and multi-pack training session that will be held in May. So please visit there to get more information. And if you'd like more information about your own materials and which sputter profiling characteristics or guns might be best suited for your application, please contact us. We also ask you to subscribe to our LinkedIn and YouTube pages, and you can find links to those at the bottom of our website.